All right, let's dive into some pretty mind-bending stuff today. We're going to be tackling quantum theory,
Okay.
specifically the famous Einstein-Podolsky-Rosen argument, or EPR.
EPR.
You being a philosopher, I think you're really going to love this.
Yeah, EPR, it's not just some dusty physics problem.
Right.
This debate is alive and kicking even in fields like quantum computing, which might seem pretty far from philosophy at first glance.
Exactly. And we've got a fantastic source for this deep dive, a Stanford Encyclopedia of Philosophy entry on EPR.
Oh, cool.
So what's the mission today?
Well,
We're going to unpack EPR, the argument itself, the assumptions baked into it, and why it still matters even if our listener doesn't have a physics degree.
right. So let's start with the thought experiment at the heart of it all.
Okay.
EPR imagines two particles entangled in a way that links their properties. Think position and momentum. They're like a perfectly choreographed dance duo, even when separated by vast distances.
So if we measure one particle's position, we instantly know the others, even if they're light years apart. That's what Einstein calls spooky action at a distance, right?
Precisely.
Okay.
And the spookiness is where the philosophical rubber meets the road. EPR presents us with a dilemma. It argues that if we want to hold on to two very intuitive ideas,
Okay.
we run smack dab into a contradiction with the way quantum mechanics describes the world.
I'm intrigued. What are these two intuitive ideas that EPR throws into question?
So first there's locality.
Okay.
The idea that something happening here can't instantly affect something way over there.
Yeah, seems pretty reasonable.
The second is the completeness of quantum mechanics. EPR asks, is quantum mechanics the whole story, or is there something missing in its description of reality?
So either we toss out locality, this idea that effects have to travel at finite speeds,
Right.
or we admit that quantum mechanics is missing some piece of the puzzle. Is that what Einstein was getting at?
Well, Einstein wasn't necessarily saying, here's the missing piece. He was more like, look, if we assume locality is true, then the way quantum mechanics describes these entangled particles just can't be the whole picture. It was a challenge, a no-go argument, pointing out the tension within quantum mechanics itself.
Fascinating. So we've got these entangled particles doing their spooky dance, and Einstein saying something's fishy with the whole picture.
Right.
But how do we actually test this? How do we go from a thought experiment to something we can investigate in the real world?
That's where David Bohm's work comes in.
Okay.
He reframed EPR using the idea of particle spin, which is basically the direction of a particle's angular momentum.
Okay.
It's easier to grasp than position and momentum.
Why was that reframing so important? Was it just to make things easier to picture?
Well, it was more than that. Using spin, we can actually design experiments instead of two particles miles apart.
Okay.
We can think of them as tiny spinning tops. Measuring the spin of one instantly tells you the spin of the other, no matter how far apart they are.
Okay, so Bohm gives us a way to take this out of the realm of thought experiments
Yeah.
and into the lab. But how do we design an experiment to see whether quantum mechanics is giving us the full story or whether we need to rethink locality?
Well, that's where John Bell and his famous theorem come in Bell's work. Provided a way to test the assumptions behind EPR, especially the assumption of locality.
Okay.
He came up with a set of inequalities now called Bell inequalities.
So Bell gave us a tool to pit Einstein's intuition about locality against the wild predictions of quantum mechanics. It sounds like these inequalities are the key to figuring out who's right.
Exactly. If the world is both local and realistic, meaning that particles have definite properties even before we measure them,
Right.
then Bell's inequalities must hold true. But if quantum mechanics is right, and these spooky correlations are real, then the inequalities would be violated.
Okay, I'm on the edge of my seat here. What happened when scientists actually ran these experiments? Did they vindicate Einstein's belief in a local realistic universe? Or did they side with the strangeness of quantum mechanics?
Well, the results were pretty mind-blowing. Experiments started showing violations of Bell's inequalities. It was like the universe was telling us that our everyday intuitions about locality might need a serious overhaul.
Hold on, are we saying that Einstein, the genius who revolutionized physics, was wrong about something as fundamental as locality that's a tough pill to swallow?
Well, it's not quite that simple. The early experiments did have some loopholes, potential flaws that left some wiggle room for local realism to maybe possibly still be true. But as the experiments got more sophisticated, those loopholes were closed one by one.
So what were these loopholes and how did scientists manage to plug them? It sounds like they had to get pretty creative.
One was the detection loophole.
Right.
Our detectors weren't perfect. Think of it like a fishing net with holes. Some fish will always get through, making our catch inaccurate. To plug this, They developed more efficient detectors, catching more of those entangled particles.
Okay, that makes sense. But what about the locality loophole you mentioned earlier? How do you make sure those particles aren't secretly communicating faster than the speed of light?
Yeah, for that, they had to get really good at separating the two parts of the experiment, ensuring no signal could travel between them faster than light. We're talking kilometers sometimes, even using fiber optic cables to make absolutely sure.
So even with these loopholes closed, what we're left with is quantum mechanics wins.
Hmm.
Einstein's intuition loses. I have to admit, it's a bit unsettling to think that something happening here could instantly affect something light years away.
It's definitely a challenge to our classical worldview, but here's where it gets really interesting for you as a philosopher. The EPR paradox isn't just about physics. It throws open some of the biggest philosophical questions about reality itself.
Okay, I'm all ears. How does this seemingly obscure physics problem connect to the big philosophical picture?
Well, think about it. We tend to assume that objects have definite properties, whether we're observing them or not, like that coffee cup is on the table, even if I close my eyes. But EPR and the experimental evidence supporting it suggests that at the quantum level, things might not be so straightforward.
So are we saying that a particle doesn't have a definite location until we measure it, that it's somehow in multiple places at once? That's pretty wild.
That's one way to interpret it, often associated with Niels Bohr and the Copenhagen interpretation of quantum mechanics. It suggests that properties like position only become definite when we measure them. It's like saying the act of observation somehow participates in creating reality.
Whoa, hold on. That's a huge departure from our everyday experience.
Yeah.
Are there other ways to understand this? It feels like we're venturing into some pretty metaphysical territory here.
There are other interpretations, each with its own set of philosophical baggage. Some, like the many worlds interpretation, suggest that every time a measurement is made, the universe splits with each possible outcome playing out in a separate branch of reality.
Wait, are you saying there are infinite versions of me out there living out every possible choice I could have made? That's a lot to wrap my head around.
It is a mind-boggling idea, but it's one way to grapple with the implications of non-locality if we accept that actions can have instantaneous effects across vast distances. It forces us to reconsider the nature of cause and effect, the flow of time, and even the very idea of a single objective reality.
Okay, so we've got Copenhagen, where observation creates reality, and many worlds, where reality is constantly branching off into parallel universes. Are there any interpretations that are a little less, well, radical?
There are, but they come with their own set of challenges. For instance, Bohmian mechanics tries to rescue the idea of particles having definite properties even when we're not looking.
So in Bohmian mechanics, the particles have a definite position all along. We just don't know it until we measure them. Does that mean locality is safe and sound in this view?
Not quite. Bohmian mechanics still requires non-locality. It introduces this idea of a quantum potential that connects entangled particles, allowing for instantaneous influence across any distance. It's a way to have your deterministic cake and eat your non-local pudding too, so to speak.
It seems like no matter which interpretation we choose, we're left with some pretty profound philosophical mysteries. EPR really is a gift that keeps on giving more questions than answers. What do you think are the most important takeaways for a philosopher like our listener considering all of this?
I think EPR highlights a crucial tension between our everyday intuitions about the world and what quantum mechanics seems to be telling us about reality. It forces us to re-examine some of our most basic assumptions, like the idea that objects have inherent properties independent of observation.
So EPR isn't just about physics. It's about how we understand the nature of reality, the relationship between observer and observed, and even the very limits of what we can know. It's a call to rethink some of the most fundamental questions in philosophy.
Exactly, and I think there's another important lesson here, one that goes beyond the specifics of EPR. Even our most cherished scientific theories are provisional. They're subject to revision as we learn more about the universe.
You're saying that even Einstein, the most iconic scientist of the 20th century, could be wrong about something as fundamental as locality. It's a humbling thought.
It is, and it reminds us that the journey of scientific discovery is never truly over. There's always more to learn, more to question, and more to wonder about.
It's incredible to think that a thought experiment conceived almost a century ago can still have such profound implications for both physics and philosophy today. It makes you wonder what other hidden gems might be lurking within our current scientific understanding, just waiting to be unearthed.
Absolutely, and it highlights the vital interplay between physics and philosophy. We need both to make sense of the universe and our place within it.
And it's amazing to think that EPR has gone from, this heady philosophical paradox to something with real-world applications. We touched on this earlier. quantum computing and cryptography.
Mhm.
Those fields seem a world away from these abstract debates about the nature of reality.
It's true, the very entanglement that was giving Einstein sleepless nights turns out to be an incredibly useful resource in quantum information science. It's like the universe was hiding a secret weapon right under our noses.
So the spooky action that Einstein found so objectionable is now being used to build super-fast computers and unbreakable codes. That's quite a twist.
It is. In quantum computing, entanglement is the key to creating algorithms that can tackle problems that classical computers could only dream of. Imagine simulating complex molecules to design life-saving drugs or cracking the toughest encryption codes to ensure cybersecurity.
It's almost poetic. This thing that challenged our fundamental understanding of the universe is now being harnessed to push the boundaries of technology. It really underscores the unpredictable nature of scientific discovery, doesn't it?
Absolutely. What starts as a purely theoretical debate can end up changing the world in ways we never anticipated, and it reminds us that supporting fundamental research is crucial, even if we can't see the practical applications right away. Who knows what other mind-blowing technologies are hidden within the equations and thought experiments of today?
Yeah, it's a great reminder that we're still just at the beginning of our journey of understanding the universe. We've covered a lot of ground in our deep dive into EPR, the history, the physics, and the philosophical implications, but it feels like we've only scratched the surface. What do you think our listener, a philosopher at heart, should really take away from all of this?
Well, I think EPR isn't just a puzzle to be solved. It's an invitation to rethink our assumptions about the world. If something as fundamental as locality can be called into question, what other seemingly unshakable beliefs might we need to reconsider? It's a call to approach the universe with humility and an open mind.
It's also a testament to the power of thought experiments.
Yeah.
Einstein and his colleagues, through sheer intellectual wrestling, managed to uncover something so profound about the nature of reality. It's inspiring, really.
It is, and it shows the deep connection between physics and philosophy. They're not separate disciplines. They're partners in this grand quest to understand the universe and our place within it.
Well, on that note, a huge thank you to our listener for joining us on this wild ride into the mind-bending world of the EPR paradox. Keep those sources coming. We can't wait to dive into your next intellectual treasure trove.
Until next time, keep questioning, keep exploring, and never stop being curious.